Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to welcome Shivnath Babu, who's an assistant professor at Duke University. Shivnath did his PhD from Stanford University in 2005, and since then he's been at Duke. He's already been the recipient of 3 IBM Faculty Awards and the NSF Career Awards. He also has, I guess, in this last SIGMOD, his work on the iTuned system, which he'll talk a little bit about today, won the Best Demo Award. And so with that, Shivnath, we'd like to hear from you today on the experiment-driven system management.
Thanks, Vivek. So experiment-driven system management is some sort of a methodology that we have been working on for quite a while now, around 5 years now. And let me first introduce some of the type of problems that we are trying to target with it. So one very common problem that sort of shows up in database management sort of a context is this problem of tuning problem queries. Okay? So imagine you have a complex query, maybe it is part of a report generation workload, there might be some requirements on it, and if the query is actually not running fine, right, there might be a user or a DBA who might have to tune it and then probably improve its performance by some factor. This is commonly called the SQL-tuning task. So what ends up happening in these contexts when you have a specific query that you have to tune up, and what the DBA might do, a usual course of action is to actually collect some monitoring data. And it might include, in the last scale, monitoring data might include when looking at the plan, what different operators, the number of records the different operators are returning. In fact, we actually do a lot of work with PostgreSQL. And if you're familiar with PostgreSQL, you know that if you do this explain analyze for a query, it actually shows you information which can be picturized like this. It shows you the plan, the operators, it shows you the estimated cardinality, that is the number of records the optimizer thought that operator might return, and the actual cardinality. And after looking at something like this, you might realize, so look, this is hash join where the optimizer thought only 100 records are going to come, actually 700 records are going to come, and there might be a hypothesis the DBA might actually have is just replacing that index nested loop join with the hash join might actually improve performance. Or sometimes it might be looking at these things, actually changing the join order might improve performance. And you might give hints to actually force such plans and whatnot. But the main point here is to actually achieve such a task, to really tune the query from problem identification to actually getting a fix and putting in the system. A lot of runs might happen, runs of plans like this, to observe, to collect more monitoring information, to actually sort of validate some of your hypotheses, and finally, once you have found a fix, to validate that new plan actually works before you can put it in the production system. Right? Another domain, parameters. And many database systems, actually most database systems, have these tuning parameters. Sometimes they are called configuration parameters, sometimes they are called server parameters. There are these parameters that control buffer pool sizes, I/O optimization, the block sizes, at what rate to checkpoint, parallelism, the number of concurrent queries you can run, lots and lots of parameters to tweak the optimizer's cost model. With a system like PostgreSQL, again, we have done a lot of work with this. We have identified that around 15 to 25 parameters, depending on whether it's a read-only or lab sort of setting versus OLTP setting, can actually have significant impact on performance. And I think for most database systems, not just PostgreSQL, it can be a very frustrating experience to tune these parameters for good performance. And there are no good holistic parameter tuning tools available, and for a good reason. So here actually I'm trying to summarize a problem that vexed us for a long time, which actually got us into this whole parameter tuning game. So what I'm showing here is a response surface. So there are 2 axes, independent axes. This parameter here, whose value is in megabytes, is the main buffer pool setting in PostgreSQL. Okay? And this one is actually, it's an advisory parameter where you're telling the PostgreSQL database system, look, there is such and such value of operating system buffer cache. It doesn't, you can really lie. Nobody's really going to check that. So we actually varied these 2 parameters. In fact, we varied many more. And what is being visualized here is the performance for a workload, which here is just one single query in TPCH. In fact, for even a toy database setting, if you can actually call it that. 4 GB TPCH total database size, 1 gig of RAM, a 1:4 ratio, and in fact, this whole database is running inside a Zen virtual machine, right? So what actually what sort of got us in here is we were running the system with a sort of parameter setting that was advised by the community, which kind of says, look, set your shared buffers to around 1/4 of the total memory size, and then giving some memory to the operating system, set this value to the remaining. So that kind of gets us into a point over here where performance is really bad. And this actually was IO, the IO was really, the system was IO bound, and we could see that, right? So the natural thing you would think of is increase the buffer pool size, and that will improve performance. We did that, and performance became worse. So it's like we are not seeing the surface. We are just tweaking things and then observing performance. That got us to generate this entire surface. And you can see once the surface is generated, there are some regions where performance is good, some regions where it's bad. You can see the trends. I'm not going into the details of everything that happened, but just what I want to tell you is the moment you see this, you know that I don't have to know what these parameters are. I can set it to a value and get good performance. But how do real users, real administrators deal with problems like this? There's no model. Actually, just I want to make one point. When you're changing parameters, a lot of things can change. The query optimizer can pick a different plan. Even within the plan, the operator implementation might actually change. The impact of buffer pool settings can actually change. A lot of things can happen. Okay? If we have time, I'll drill down into how we actually diagnose the cause of this interesting behavior. So how do real users deal with this thing? They do exactly the sort of things that we were trying to do. We would vary a parameter, and often it is one parameter at a time, and try to tweak the system to good performance. And this can actually, if you think about it, this can be horrible if there are interactions between or among parameters where the impact of changing one parameter, the impact of changing, let's say, effective cache size, changes for different settings or it's different for different settings of shared buffers. Right? This one parameter at a time can actually lead you to real poor performance. So these are two examples of like how management, system management, or database management happens in the real world, where this is sort of a workflow that's happening. I realized based on the monitoring information that I've collected about the system, look, performance is bad, I have to tune it, or any general management task. I'm going to give you some interesting examples, and then you realize I have to actually get more data, and I plan some experiments that I have to do. In the context of parameter tuning, it would be running the workload for a specific database configuration, right? I plan the experiments, I conduct them, and that brings in information. And there are different types of information you can collect, process it, and maybe at the end you have enough information to achieve your task. Sometimes you don't have it, and you have to continue. This process is very, very common. And the sad news is it's very manual, very ad hoc, right? Even things like, where do I conduct these experiments? Do I run it on my production system? Actually, do I run it on my test system? What if that is a different setting? So there are a lot of things which administrators really struggle with. And the goal of this entire work is to sort of automate this process to whatever level it can be automated. Okay? So I'm going to give you some examples of how the different sort of domains where we have put this to use and tools we have built. I'm going to be spending most of my time today talking about that first one, SQL-tuning, which is the problem I introduced in the beginning, and a couple of tools that we have built there. The second one, which is the one I usually used to talk about. In fact, I was at Stanford 3 months back, and I talked about this iTuned tool. And now I'm not going to bore you with talking about the same thing again. So there was one version that we built that we are actually trying. This is the one that Vivek actually mentioned. We actually presented a demo on this iTunes system at Sigmod, and we are doing some more work on that. It turns out this sort of tuning problems actually appear in the Hadoop MapReduce setting. So this is one simple response surface. I'm not going to drill down to it, but with Hadoop today, with each job there are around 190 configuration parameters. Just like in a database system, around 10 to 15 of them can be really crucial for performance. There are interactions and whatnot. So this is something that we are actually studying and building a tool on. One of the problems that we attacked at the very beginning, and a very common problem that we see, is this whole notion of benchmarking or capacity planning, where administrator might have, again, some, so this is actually for a storage server, where we are varying it as running the NFS file system. We are varying the number of NFS daemons and the actual number of disks in the storage system. You can see that some performance aspect is being measured. You can see that this dimension has a big impact, this dimension doesn't. So in benchmarking, often people are interested in capturing either some map of how performance will be, or which parameters are important, right? People spend a lot of time doing this. In fact, to even report TPCH performance numbers, you might spend a lot of time doing something like this. And what we realized is often you don't really need this exact surface. It can take months or even days to actually generate this. Giving a quick approximate surface can often be very, very useful, or identifying important parameters. And we did some work which we call cutting corners, right? Ideally, you should be generating the surface, but you can cut corners and get an approximate version. That's often good enough, and at like 1/10 or even smaller amount of time. Another problem where we have attacked is this thing which I'm calling interaction-aware query scheduling. So we all know that although query optimizers generate plans looking at one query at a time, the moment multiple query plans are running together, who knows what's going to happen? Maybe they actually help each other out. Maybe they beat up on the same resource. Performance can be poor. A scheduler that's aware of these interactions can do a really good job. But how does it know about this different interaction that can arise when queries are running in a mix? So for that, you need models. Now, who's going to give you these models? The only way you can actually do that is to run, for your hardware system, for taking different mixes, run some of these mixes, observe, and build the models which will work in your context. Nothing will generalize, right? So we have attacked actually that, again, using running a mix, collecting information, selecting which mixes to run, because the base of mixes is huge. Experiment-driven management works really great. And another one we are actually focusing on now is data in a database system or in a file system can easily get corrupted today, because people run things on commodity hardware where hardware can actually be very flaky. There is the firmware bugs, network interface card bugs, or operators actually can make mistakes. So because of a lot of reasons, data can get corrupted. And we had this very interesting example. I'm not going to tell you where it is from, but there was a critical application which it is actually crashed, and it couldn't be brought up for a long time, literally a long time, because what had happened was that corruption had kicked in. Somewhere the data for that application had become corrupted. Backup and disaster recovery, everything was in place. The backups also became corrupted because nobody was really checking, right? And the application crashed. We tried to bring it up from the backup, and the backup is also corrupt. So literally, a lot of data was actually lost because of things like this. And again, how do we attack something like this? There are data integrity checkers, because there are checksums, there might be lost writes. There are things that you can actually run to detect it and give advance warning to administrators. So that's, again, another interesting domain which we are actively working on, where this whole experiment driven, because you're running tests, you're getting some information about the test results, and then figuring out maybe if this snapshot is wrong, there's this file system issue, maybe the database might also be corrupted, can actually bring in and do some interesting information. So after building a whole bunch of these things, what we realized is there's actually a lot of commonality. All of these are independent tools. There's a lot of commonality in, for instance, at the level of maybe scheduling experiments, maybe the whole infrastructure, the harness to run experiments. A lot of commonality in the planning algorithms. So we are trying to raise the level of abstraction even to the level of a language. And I don't know how much time I will have, but I'll try to at least give you some of the main ideas. And the way I usually do these talks is I pick one system after having given the overall vision, right? I pick one tool that we have built, and then use that to sort of as an end-to-end thing to illustrate the different aspects of experiment planning, running, the harness and everything. And what I've chosen to do today is this Xplus SQL-tuning aware query optimizer. And at the end, I'll actually talk more about, depending on the time I have, some of our current focus. So this is the same problem I introduced in the beginning. You have a problem query that you'd actually like to tune, or the admin. He needs to improve the performance by some factor. And what happens today, actually a lot of this just happens manually, where they do things. Won't be great if the administrator could instead pose a question back to the database system. Look, I have this query I have to tune. Okay? Can you, and I'm not happy with the current plan, right? I need to improve its performance. Can you generate a better plan for me? So this, it turns out, is actually one small part of this overall SQL tuning. Sometimes by rewriting the query, or sometimes by adding more indexes, or sometimes by tuning these parameters, you can improve performance, right? You can actually fix this problem. But all of them are invasive in different ways. Adding an index can actually affect the performance of other queries. It can affect workloads, right? The update ratios and things like that. So we focused on this a smaller piece of the problem, and what we are able to show is if you can't find such a plan with some caveats, it sort of means that there is no other go than some invasive tuning. And what we have built is a new optimizer which supports the regular optimization. The optimizer's goal is given a query, generate a good plan, right? It supports all of that, but it supports the notion of what we call tuning sessions. So in a tuning session to our system, the inputs that are given are, of course, this query, for which performance is not good. If you have the plan, the current plan for which performance is not good, you can give that as well. We actually sort of assume that is available as of now in our current prototype. And then these tuning objectives. So we support different tuning objectives like improving performance by some factor, or I have 1 hour. I need a better plan in an hour. You find the best plan you can find in an hour. So we support multiple tuning objectives. And the way Xplus actually works is by carefully choosing some plans or some subplans of this query to run. It runs them, collects information, and iterates. It's basically applying that same old experiment-driven methodology. Okay? And because it's running plans, we always have, our tools always have this, the number 3, the resource constraints part, which is, so tuning is going to place some overhead somewhere, right? The admin or the user would like to specify under what constraints. The typical thing there might actually be, I'll give you an example. So one very simple example is if you have a database system that has a multi-programming level of 10, you can use one of those slots to run a tuning subplan. Right? Just one very, very simple example, but somehow you want to limit the overhead of tuning. This type of tuning is not free. It's going to place some overhead somewhere. Maybe it's in the cost in the context of a cloud. Maybe the admin might say, it is possible in a system, look, I have $10 to spend an hour. You can get resources on the cloud on EC2 and do whatever. Right? So there are different types of interesting resource constraints and an entire harness that we have implemented for 3. So just to give a quick example so that we are all on the same page. So assume this is a subplan that our system chooses to run for this particular query, hash join on 2 tables. So even before the subplan is run, we can have the estimated cardinalities as estimated by the optimizer, number of records that are going to come out. At the end of the run, we actually collect 2 pieces of information. One is the actual cardinality, how many records were produced by that operator when it ran. And then something which we call estimated actual cardinality. So it's this, the 670 is actually if the query optimizer knew that the table scan on R and table scan on S are going to produce 1050 and 850 records respectively. This would be its estimate, not this. So if you see this, the 670 is pretty much close to 700. What that means is for the join, you also have to estimate the join selectivity, right? Not just the input cardinalities. So the join selectivity estimate was more or less accurate. And we use this. So essentially, as of now, our optimizer uses these 3 pieces of information. We have much more because when we run this, we can observe how much I/O happens, the pattern of I/O, bottlenecks. These are all information we have, but we have not, in this optimizer, found a way to plug it back in a principled manner. Okay, so how does Xplus actually work once these inputs are given? It starts running these subplans, and as it is running them and collecting information, progressively it keeps on doing it. It might have better and better plans. So what I'm actually showing there is the cost of the best plan found so far. This cost sort of keeps on going down. This is not the cost of the best plan as estimated by the optimizer at any point. Its performance can actually become worse because the optimizer is mixing accurate cardinalities with estimated cardinalities, and sometimes that may not be a good thing. Often, I shouldn't say often. Sometimes it's not a good thing, right? The user can actually stop this at any point, say, oh, I'm happy with this plan that was found, or run it to so-called completion point, where we are able to provide a sort of a strong optimality guarantee. Okay? So I'll tell you actually when what happens or under what conditions we reach this point. It can be reached relatively efficiently, where we can say, look, the plan I have found so far, the best plan I have found so far is indeed the optimal plan for the current database configuration, and that includes the current physical design indexes, the current server configuration parameters, all the logical configuration, and the current hardware, the physical configuration, what resources have been allocated to it. So we are not changing that. We're not playing any games with that. and each and every plan costed using accurate cardinality values. So every plan has now been costed by the optimizer using accurate cardinalities, no estimates. So if you're willing to assume that, and this is actually at least in DB2, they have some results verifying that, and we have, to some extent, we have done this for PostgreSQL2. If the accurate cardinalities are given, the cost models do a relatively good job in a relative sense, finding the best plan, or ordering the plans in the right manner, at least the good plans. So this is again something which we definitely want to take out, because sometimes the cost model can be inaccurate, right? All the parameters and the cost formula you actually plug in, but that's not been such a big problem so far. The main reason we have the first one is, again, as I said, we want to be non-invasive. In the sense we want to actually suggest a fix that will work with the current setting. Right? But there are other pieces of work which actually deal with that too. In fact, all the parameter tuning work. Getting the plan right is really the first, the most important thing for performance. Parameter tuning, all of those things are secondary to some extent. So there has been actually a whole bunch of interesting work, and well, some of the main challenges in this context are which subplans you are going to run, where do you actually run them, and bound the overhead of tuning on the production workload. There has been interesting work in this domain. The pay-as-you-go work done by Ravi and Surjit and Vivek right here at MSR. So we have actually separated our work from some of the earlier work, the query execution feedback work happening for some practical reasons. One of the main ways in which we separate our work is we are very focused on a query. So the DBA or user has given us, this is the query I want you to tune. And that is the sort of context we see in the PostgreSQL community. Right? Often, 95% of your queries work fine. There are some of these killer bad queries. We actually focus on that. Right? And we have very consciously chosen to separate these so-called tuning sessions from the regular optimization for more or less the same reasons. And another important reason is, I was having this discussion with Ravi. He was telling me that even if you bring in this query execution statistics and put it back in, there's no guarantee that the plan optimizer will actually find when some accurate cardinalities and the rest has been estimated. There's no guarantee that that plan will actually be better than the previous plan. Right? So there's a lot of trial and error, funny things that can happen. So we have chosen to separate these things out. Right? They're clearly separated out. Tuning sessions, you use it and when you know how to use them and when you really want them. And another thing, and this is some feedback that we got when we presented this work, the very first version of this work more than a year back, the DB test workshop in 2009, so we are sort of proposing a whole bunch of changes, right? People, like at least from the commercial database perspective, the more changes you propose to what is there, the less likely it is going to actually be adopted. So we definitely, since we are working on the optimizer, we want to make 0 changes to the query execution engine. And interestingly, I'm actually also going to tell you how we get away by making 0 changes to the commercial or database query optimizer. It might sound weird, but there's a way in which we actually do that. Okay? So this whole problem and some of the ideas that we use, especially running plans and using feedback, is not really new. What I'm going to spend a lot of time focusing on is this big challenge of which subplans from this large space of plans to actually run to reach your tuning goal. Okay? And the main, if I were to abstract out the one single main idea in Xplus, is actually how we treat this overall physical plant space. So imagine this were to be your entire space of physical plants. So P1 through P8 are different physical plants. We actually try to group these plants together into what I call plant neighborhoods. Okay? And the plants in each neighborhood are related in some specific manner. There are some relationships that we want to exploit. So, excuse me. The key to this is the notion of a cardinality set of a physical operator or a plan or a neighborhood. Okay? So let me explain what a cardinality set is. So consider this simple, actually is an operator hash join that works on 2 tables. It's a filter on one of these tables. So the way in which the query optimizer estimates the cost of an operator like this is it has some sort of a cost formula to which you need inputs, and some of the main inputs are the expressions and especially the cardinality values for the expressions. Let me give you an example, right? So for this hash join in PostgreSQL, the to estimate the cost of the hash join, the optimizer needs the sizes of its inputs. So in this case, the expressions are the sigma of R and S, right? For these expressions, it needs this blue, the Cardinality values, and it plugs that in along with some other parameters like all of the environment representing ones, the buffer pool size and estimate cache size and all of this, and estimates the cost. Okay? So we define the cardinality set of a physical operator as the set of relational algebra expressions. This is expressions, not values. Okay? And this is a distinction I just want to emphasize. So the expressions whose cardinalities are needed to cause that operator. For a plan, again, you can sort of extend, right? I've just laid out the plan, and again, for a plan, there will be for each operator, there will be a set of expressions. Take the set union of all of these expressions, and you get the cardinality set of a physical plan. Again, expressions, not values. And once you can associate a set of expressions with a plan, you can actually say, look, I'm going to divide up, I'm going to sort of cluster this set of plans based on equality of cardinality sets. Okay? I'm going to use a simple definition. In fact, we actually have a more sort of complex definition of plan neighborhoods because we want to minimize the number of neighborhoods. We want these neighborhoods to be as large as possible, each neighborhood to be as large as possible. But to keep things simple, I'm going to assume for this talk that our definition is a neighborhood contains plans all of which have the same cardinality set. Yes, Ravi.
I think the complex. You discussed multiple problem formulations, right? Find a plan that is 20% better, or run for an hour, or you say find a plan with all accurate cardinalities. So under what problem setting are you discussing that?
Under all of them.
It applies to all of them.
Yeah. Because the objective, this is really the structure, the abstracting the plan space. Now I have to talk about how does the optimizer make progress for a particular tuning goal. That's where all of these other things come in. Okay, any other questions? So the intuition here is, simple intuition is, well, if I have accurate cardinality values to cost one plan in a neighborhood, I can cost all the other plans accurately. Right? This is the relationship for the simple model. And naturally, so our notion of a cardinality set of a neighborhood, which is trivial here, is the union of the cardinality sets of all plants in that neighborhood, which again is trivial here because all plants have the same cardinality set. Okay? A simple example, two plants which look different, but in reality have the same cardinality set, at least in PostgreSQL. This plan is a three-way join with some filters and a couple of hash joins. This one exactly over the same table, same filters. There is a hash join replaced by a merge join. There's a hash join where the order has been flipped. So these sort of things don't really affect the cardinality set. Right? So a single cardinality set actually consists of a whole bunch of different plans.
The only variation between plans within one neighborhood would be the physical operators, and ordering of operators.
And commutativity. But it's really a function of your, the optimizer's cost model. Yeah. So that's exactly right. So basically within the same, at least with PostgreSQL, within the same neighborhood, essentially all possible replacements of operators, which also include indexes and things they access, and the commutativity. So this will define that neighborhood. In fact, we use transformations to generate plans that way within the neighborhood.
How is the plan different from the memo group?
How's the so we are really talking the level of physical plans, not really the logical one. So if you're talking at the level of an expression, then, so if I were to, I think that's basically one way to characterize it. So memo group, as I understand it, is really a logical sub-expression. Okay, well, so once we have these neighborhoods, now we are starting to talk more about the, yes?
In answering his question, you did not emphasize the equivalence class of complexity that you're taking. A typical memo group does not. And I thought that was the fundamental.
I think the memo group is actually sort of representing all possible physical plans for that logical expression.
They're just different plans, but they are not quantifying complexity except through this physical cost. you with denoting the expression which is affecting the cardinality, you are creating an equivalence class with that property. You created a homomorphism of sort with respect to the cardinality, and that is a stronger notion than a typical memo group that you have in implementation.
Okay. Well, put it stated that way. Essentially, the grouping is all sort of plans which can be costed using the same set of cardinalities.
What is the difference from memo group? Isn't it just captured by the set of different join orderings and?
No, it could be that. Just to give you an example, Ravi. So assume. So if instead of the merge join, there was an index nested loop join, right? To cause an index nested loop join, at least in PostgreSQL, you need not know the actual size of the number of tuples on the probing side or on the index probing side, right? You only need to know on average how many records are fetched per probe. Yeah. So the moment we start talking of physical versus logical, there are.
It's a finite grouping.
It's a finite grouping. Yes. Yeah. Okay. So now we are kind of why all of these neighborhoods, right? The main reason is the way Xplus sort of makes its progress as it's trying to tune the query can be characterized in terms of how it goes about what we call covering neighborhoods. So a neighborhood is said to be covered when accurate cardinality values are available for all expressions in its cardinality set. Yes, so if a neighborhood is covered, then all plans in it can be costed accurately as per the optimizer's cost model, right? Now you can think of this sort of Xplus progress. This is the picture I showed you earlier. So as Xplus progresses, imagine a physical plan space where you had 4 neighborhoods. It runs the plans, it actually might end up covering this one first and then this one, and actually when it runs the plan, multiple neighborhoods might get covered together, and at the end, the optimality guarantee you get when all neighborhoods are covered. So to actually, in the process of achieving this, there are some nice efficiency and guarantees that Xplus can actually make. The first one is it runs at most one plan to get the accurate cardinality values for a neighborhood. This might seem trivial, right? Because the way I defined a neighborhood was all the plans which have the same cardinality set. But there's a subtle distinction which I'll get into a moment, because if it is the case that you can efficiently measure cardinalities for all expressions that are needed to cost the plan. So in one case we are saying these are the things you need to cost the plan. In the other case we are saying these are things you can measure when the plan runs. These are sometimes different, and I'll get to it, right? But we have ways in which we actually ensure that at most one plan. And the interesting thing is, it's often not a plan. It's actually a sub-plan. Okay? And the other thing is we have this feature where the moment a plan is actually run in a neighborhood and it gets covered, so accurate cardinality values are measured for some expressions, we have a way in which actually a data structure which enables you to find the minimal set of other neighborhoods where plans have to be recosted, because you now have accurate cardinality value for an expression there for which you only had an estimate earlier. Okay? This is just a data structure trick. Then all the neighborhoods can be covered by, so the trivial thing is to run one plan per neighborhood or subplan per neighborhood to cover all neighborhoods. It turns out, because of the intersection and putting some assumption properties and everything, you don't have to run plans for each neighborhood. In fact, you end up running very few plans. Just to give some numbers, for I think for query 9 in TPCH, there are around 36 neighborhoods, and 7 or 8 subplans need to be run to cover all neighborhoods. So it's basically, you can exploit all of these properties of a real setting to actually really cut down on the number of neighborhoods. Yes.
We did some related work, as I was mentioning. We call it exact cardinality query optimization. There we looked at the other extreme. I want to find a plan where all cardinalities are accurate. And we didn't have this notion of neighborhood, but we had a notion of something we call covering queries or plans. So the idea is, take the set of all plans in the memory, find me a smaller set of plans to run, so that if I execute these plans, I get the cardinalities for all the plans. So you may want to look at that. It's sort of related, but it's only that extreme. As you said, you have multiple versions.
Definitely. So the way I would actually state that is, if my tuning goal was to measure all cardinalities, so to get to this point as efficiently as possible, right? That's exactly the thing you would want to do. The admin knows ahead of time, I want to figure out how much I can, or what's the maximum performance improvement I can get, right? So that I can avoid all invasive things. That would be a
testing context where
Yeah, but that's how it will be. It could be applied here.
To run and to find the optimal.
Yeah.
May not be necessary.
And in some sense, after running experiments, we have come up with a similar intuition, which I'll try to characterize in the experimental results, and how, if you want to get to that point. Okay, so essentially, once the space is covered, we actually get this property. Right? Okay. So now, well, let me just take a step back and ask about. So I've kind of shown you how Xplus works at some level. So what are the challenges, right? What are the sort of technical problems that have to be solved? How do you enumerate all of these neighborhoods, right? How do you enumerate plants within a neighborhood? Pick a plant with a neighborhood to actually run our subplan, right? In terms of progress, I'm at some point. This is always the case in experimental tuning. You're at some point, you have some information, and you're figuring out what to do next. So which neighborhood to go after next, right? And once you have picked a neighborhood, which plant to run or subplant to run within that neighborhood to get the required information in that neighborhood. So I'm going to drill down into each of these questions and at some level of detail. The thing is, it has taken us around 1.5 years, or maybe even close to 2 years, and one complete rewrite to get to this point. Because a lot of this, higher level ideas might seem easy and probably even straightforward, but to actually get it to work, to really implement it in the context of a real optimizer, can actually take a lot of time. So I'm kind of trying to stay away from the details, but I'll be really happy to either talk about them if there are questions or offline. Okay? So the first problem: how do you enumerate these neighborhoods? Right? And even the enumerating plants within a neighborhood. Our first approach was to try to generate, because we are working with PostgreSQL, which is a bottom-up query optimizer, right? Generate all plants, try to apply some clustering. That just does not scale. So a transformation-based approach is the best thing in such a setting, where you can carefully select particular plants, only the plants you kind of want to explore. That turns out to be the way to go in here. And what we have done is we have actually developed a sort of a transformation-based PostgreSQL optimizer, if you want to call it that. But the critical thing is trying to write these transformations, and these are physical plant to physical plant transformations, and being able to characterize them into one of two categories. So this transformation applied to a physical plant will generate a new plant in a different neighborhood, and this transformation applied to a plant will generate another plant in the same neighborhood. So the logical, the commutativity transformations, replacing physical operator transformations with some corrections, you have to account for the physical properties. That's how that will actually fall in here, right? So changing join orders and those sort of things will actually fall in there, including pushing up filters if they're expensive filters, pushing down group bys, which we have not really done, but they will actually go in there. PostgreSQL doesn't have that, so we were lucky. So this other key question is, how do I decide at any point in time, based on some neighborhoods that have been covered, which neighborhood to cover next? Okay, let me illustrate this sort of the decision with an example. So suppose I have covered that green neighborhood N1, and I have these 3 neighborhoods. So I'm trying to decide which one to go after next. And let's say that we have found, based on the current set of available cardinalities, including estimated and actual, that P2, P3, and P4 are the respective least cost, as estimated with the optimizer, physical plants in each of these neighborhoods. And again, these are uncertain because there are mixing EC with the accurate with estimated cardinalities. Okay? And suppose it is the case that in N2 we have, when we look at the level of the cardinality set, we have in these 2 neighborhoods 2 cardinality values that are missing, right? And in here there are 3 cardinality values that are missing. So this actually kind of poses a decision, right? Should we go after N2 next? Because that is where our current cheapest plan, so to speak, exists, right? And N4, because this is current cheapest plan as estimated, the estimate could be totally wrong. Right? N4, if you were to go after N4, that's going to bring in more sort of accurate cardinality values. So it's going to convert more uncertainty or uncertain values to certain, right? This is the exploration problem manifested in SQL tuning. So in this, the exploration problem is really like I have some variables for whose values I have some estimates as of now. Okay? And I'm trying to make a decision based on that. So exploitation would be, I sort of say, I ignore the uncertainty, or the extreme exploitation would be, I say, I ignore the uncertainty, I assume these are all accurate, and then go with my decision. In this case, that would be the going after the current cheapest plan. Exploration would be, I realize there is uncertainty, and I try to sort of resolve that uncertainty. Okay? And there are multiple, and this is actually, it took us a long time to sort of converge on some sort of an architecture here. And our current sort of best solution is sort of an extensible solution where we use this idea of experts and a selection policy. Actually a well-known technique in this entire area. Yeah.
Kind of cover benefit by cost.
Why don't you?
You just mentioned, right? The cost of running the plan,
Yeah.
the benefit in terms of how many neighborhoods it covers.
So that can be done, right? And I think this is where we, in some sense, right, when we present this first level of work, the sort of feedback we got is there are some standard techniques that people use when they are going after sort of tuning. They look at, they kind of look at join selectivity values or the values that sort of come out, and based on that they figure out, oh, this actually seems like a better join order for me to try next. So there are, in some sense, right?
It's more tunable using experts and using some prior knowledge.
Yeah, well, I'm not actually going to come in and say, look, this is the approach we have is the best, right? But from a practical standpoint, we probably have to try multiple things. And I think our first one was really, or at least my thought, was on similar lines, trying to actually capture the benefit, because in the whole previous line of work on iTunes and everything, that's exactly what we have done, trying to quantify benefit based on the uncertainty and coming up with even a closed form and going after that.
And how many neighborhoods did the plan cover?
Actually, in some sense, when you see the solution, something like this is what we have. So this notion of experts is really, each expert, actually, let me show you this thing. So 2 experts you can think of are exactly what I showed you in the previous slide, which is the pure exploiter is always going to suggest that neighborhood where the least cost plan lies. Go after that, right? And the pure explorer will actually go after suggest that neighborhood where the maximum number of uncertain cardinality values are. You can actually make them fancy. You can try to get some idea of the uncertainty and confidence intervals and whatnot, which actually get pretty hairy. You can actually take them, you can implement other versions of these experts, and our system is purposely for that reason is very extensible. Okay? And there's going to be a selection policy that is sort of going to arbitrate among these experts. So the challenge in this sort of an architecture would be to figure out, for instance, for SQL Server, what would be a good set of experts. And even sometimes it could be that as a optimizer developer, you might actually see cases that are coming to you for resolution, but you see a specific type of scenario where the optimizer is making a mistake. So there's nothing preventing you from writing a new expert that can see that scenario and suggest a good strategy for that setting. We have sort of converged on this architecture primarily because in that, I guess in that DB test workshop, we were talking to real optimizer people from Sybase, and they sort of led us in this direction. But I'm not going to say that this is the approach you should take. More, what I want to sell is this overall experimental methodology being applied to solve a real problem. Okay? And of course, you can actually have other experts which have some notion of some mix of exploitation and exploration. Right? And again, I don't have the time to get into the details, but these 2 sort of experts sort of look at, in fact, the join shuffler, for instance. Remember the estimated actual cardinality I kind of showed you some time back, where the looking at the particular operator, and after having gotten the accurate cardinality values for its children, you can ask the question, if the optimizer were to know the accurate cardinality values of his children, then what would be his estimate of the cardinality of that operator, right? So this sort of takes into account what is the error. You can compare estimate accurate cardinality with accurate cardinality and get an idea of which are the joins for which the optimizer either thought the join was less selective than it is, or the other way around. And these guys take that type of information into account to suggest a potentially better join order. Okay? And then there's a selection policy. So once you have these experts, you're actually picking, they are each suggesting their neighborhoods, which expert to go after at any point in time. And there are again standard things you can actually apply. The more fancy one would be a reward-based selection policy, which sort of keeps history of how good the experts were in the past and tries to pick an expert which was actually working better in the past. Okay, so that brings us to this other problem of, once I have decided I'm going to go after this neighborhood, which plan or which subplan to pick in that neighborhood. So in a sense, the way we have caused this problem is we're saying, look, I want to actually find a subplan to run in that neighborhood, which will bring in the unknown cardinality values as efficiently as possible. So if you imagine this were to be a plan in your neighborhood, and as of now, the set of based on all the cardinality values for which you have accurate, cardinality expressions for which you have accurate values. Let's say that the only ones that are missing are S and the join of R and S. In which case, of course, you don't have to do this part of the plan, right? So there's essentially a subplan identification which will kind of bring in the values you need. And this other issue that I mentioned is, imagine this were to be the current plan that we are considering in this neighborhood is actually an index nested loop join. This turns out to be the cheapest plan. Index nested loop join is not going to give you the cardinality of S, right? Because it's never going to scan this entire thing, it's just going to probe it. So there are some tricks you have to play depending on the complexity of the execution engine, and we have decided not to make any changes to the actual execution engine and do everything from the outside. So what we will do is we will go through each plan in this neighborhood and find which is the smallest subplan with required modifications. In fact, we treat the subplan as also a modification, which will bring in the cardinality values that we need. That's roughly the problem in this scope here. Okay, so that brings me to the last part of Xplus, which is the architecture and the implementation. Since I'm running out of time and I see I have 10 more minutes to 2:30. Is that fair summary of? Okay, so the architecture looks pretty much similar to all of the modules I introduced. There is something for experts and selection policy. There is the state repository that you have to keep where you're getting all of these values. There's the component that once a neighborhood is identified, picks the plan with the modifications and whatnot. There's the plan costing and enumeration, and this part is really the once a plan has been picked or a subplan has been picked, the part which is actually going to run that subplan and collect information, right? So this is really tied to this other infrastructure that we developed, where you can, if you want, you can run your experiments on the cloud or on a test system or on the production system. This is a separate entity, and Xplus can actually, essentially think of it, this part as farming out the plants, and this guy actually running it, scheduling it whenever possible, and giving the information back. And the control is the thing that is driving everything, and we have implemented a number of different controllers. So this is the architecture. We have implemented this entire thing for PostgreSQL, and the hope is to release the code. PostgreSQL, unfortunately, we did it for 8.3.4 version. They released 9 recently, and they've actually changed the. There was this interface that we had implemented to. I think it'll become clear when I show you something else. So we wanted to make it usable for PostgreSQL. That is the main area we are actually been focusing on because it's open source. But I would definitely like feedback on whether something like this would be interesting or useful in the case of SQL Server. One important sort of feedback we got, in fact, it was posted as a challenge to us. So the folks at DBTest actually told us, look, if you are going to change, going to propose this architecture for an optimizer, look, nobody's going to take it. It looks horribly complex, right? But if you are willing to sell us a tuning tool, which lives with the current optimizer, and maybe you start your life as a tuning tool and then slowly incorporate it into the optimizer, that we are willing to take. So that actually, we kind of changed the architecture, and what we have now is essentially this optimizer runs as its own Java application. It's a tuning tool that you can use, and there's a specific well-defined interface, which essentially looks like this tool needs the ability from the database to actually give it plants and get the costing, get the plants costed, maybe with some accurate cardinality values I can give you, and also execute a plan. And implementing this in Postgres required some changes to the parser, and they have sort of taken that part out. So we now have to implement a whole new parser to implement this interface for 9, and we have not done that yet. Yes, Ravi?
Does Postgres have cardinality? Can I come and give saying this is the actual cardinality value?
We have implemented that. So essentially, if you think about it, inside the optimizer, that definitely is this functionality, right? It's taking cardinality values and estimating for plants, right? What you have done is taken that internal API and sort of pushed it out. So you can call it from a client. So that's why I said 0 changes to the PostgreSQL optimizer, right? Although we implement a new optimizer. And 2 other things we have focused on a lot is the extensibility. And this system is extensible at the level of the controller. We have implemented multiple controllers. This experts controller which I described, both running in a serial mode where one expert is asked at any point in time, a parallel mode as well. We have implemented 2 pieces of related work, the IBM Leo work and the Oracle automatic tuning optimizer work. The reason we didn't implement the pay-as-you-go is we were not willing at this point to make changes to the execution engine. But if that sampling and that interface is there, I think we can actually combine these two and do, in fact, much better things, because you get more information when you run a subplan or a plan. The other thing is efficiency, because in this whole experiment-driven work, the reason our papers used to get shot down is because people would say, look, it takes a long time. Tuning parameters, or in some sense, I think mentally, it seems to me that a lot of people have this block that I want tuning, I want this recommendation to be very fast. But in reality, that's not how things happen, right? Because administrators spend weeks tuning these systems. But at the same time, that we took that as a challenge to always in our tools implement these so-called efficiency features, parallelism, subplans, and a host of other things. Right? I have a big laundry list where we have spent in a lot of engineering effort to get good efficiency. So how do we go about evaluating all of this? Well, evaluating tuning turns out is not an easy task. So we have developed a benchmark. So what we did is we pinged a whole bunch of people, including people at DB Test and our colleagues, and sort of developed this set of tuning scenarios. So tuning scenario is identified based on data and based on some potential root causes that can arise in practice, like there could be a query level issue. There's this user-defined predicate in there which is very hard to estimate its selective default, or a data level issue, skew in the data, correlation in the data. Right? Statistics level issue, some statistics may be stale or missing. Right? And physical design issues, that might be a good index that the optimizer is not taking, a bad index, whatnot. And for each of these things, there is also an objective, right? And one objective might be finding the optimal plan. So what the administrator actually wants is to find the best plan, because they're trying to figure out for the current setting how far they can, what's the best performance they can achieve, or with a specific tuning goal. Let's just say improve performance by 5x. And there are different aspects of the evaluation. Let's see some results. Okay? So so what is happening in that first row in the query 7 in TPCH. So for one of our tuning scenarios, PostgreSQL, running the PostgreSQL optimizer and finding a plan, it actually picks a bad plan, which runs in 257 and 257 seconds. Running Xplus manages to find a plan that runs in 21 seconds. Okay? There is a factor of 12 improvement, which is not really surprising because it is running subplans and actually seeing things. And the main thing which has actually taken the most time for us is getting some of the other numbers. So it actually runs for this query only 6 subplans. Okay? No full plans, only 6 subplans to tune it. And the overall tuning time is 131 seconds. So the way to look at this number, this can be a big number. But the best way to look at this number is look at the ratio of this number to that one. So how many times would that bad plan sort of have to run, and compare that with how much time it took you to actually find a better plan, or this other plan. So that normalized value is like half. So similarly, now focusing at a workload level, imagine these 8 queries where the really bad queries in your workload, and they were taking around 97 minutes overall to run. Xplus, after running, is able to cut down the workload running time to 32 minutes in 24 minutes, okay? which is around 1/4 of the time that takes you to run that workload. So the other sort of tuning aspect is where the administrator wants a specific performance improvement. Like in this case, we are actually looking at 5x improvement. Right? So Xplus, this is the same value or same scenario that we saw earlier. In half the time it takes to run that bad subplan, is able to produce 12 speed up. So if I'm looking for 5x speed up, this definitely is able to produce a satisfactory plan. Right? IBM, the Leo and ATO, because they're actually not really focused on a single query, and there are the problem with Leo, and I think this is a general problem that can arise with the query feedback setting, is what you can measure is basically determined by what plan you're running. So imagine you run a plan and you get some accurate cardinality values and throw back into optimizer, it still picks another plan in that same neighborhood. In this case, if you were to run it again, there's your monitoring opportunities actually, at least in the case of Leo, it's which as you guys pointed out is 0. So you get stuck. So Leo can actually get stuck, and it found a plan with 3.2 speed up, right? And ATO actually found one with 4.2 speed up. ATO is a more expert strategy. It runs plans for each single table, it considers each two-way join, and it goes on. It's not really scalable at some level. Okay? The other important thing why we have shown this in red is that if Leo comes and says it found a plan with 3.2 speed up, which doesn't meet my requirement here, but I don't know whether there is an even better plan. Right? So in cases Xplus, it can fail because there might not be a plan with 5x speed up, but at least you know, subject to the assumption that the optimizer cost model is accurate with accurate cardinalities, at least you know that probably now you need to invest in non-invasive tuning if you really want that speed up. And then similarly at the workload level, I'm just going to skip it in the interest of time.
So, quick clarification. In the input, let's say I come and say I want the plan which is 5x fast. Are you exploiting that value of 5x in your technique somewhere?
No, not now. But that will be something, I guess, the answer is no. But here is one aspect which might be useful to address a question that Ravi brought up and this issue, which is, so now, well, I introduced a whole bunch of different policies inside Xplus, right? It can have these 4 experts, why not have many more experts or fewer experts, which policy is actually best, right? So based on our experiments, there are, in a tuning setting, you can think of two performance metrics. One is what we call convergence, which is, I'm looking for a performance improvement, and the moment, how much time does it really take to give me that improvement, as opposed to the time to completion, which is give me that guarantee. If you think of that as completion. So the sort of short answer, because I do want to use 5 minutes to talk about some of our recent focus, the sort of short answer is, you do exploitation when you are interested in some quick improvements. But if you are interested in getting to that final point, exploitation is a bad idea. Because exploitation literally ends up making small progress. I pick this plan, I get some values, maybe the optimizer based on that will actually suggest a slightly different plan. I do that, collect some values. It takes a long time to cover that space. So in those settings, having something like, where if I know that I'm looking for the best improvement, I can tell you what is a good policy for that. There are some results which actually show that. Any questions so far? This sort of, given that Vivek has given me 5 more minutes, I want to present 3 slides to just illustrate some of the things we are thinking about. Where does this all go, given that we have been building a whole bunch of tools, iTunes and this other tool, and other things. Okay, so 3 areas that we are actually focusing on a lot. First of all, we are trying to apply to more and more, I wouldn't say more and more, but some different system management applications, which I guess as a database community, we haven't really focused on that much. And I've been talking to system administrators mostly, not purely database administrators, although they do maintain databases at both, actually primarily at Duke and a little bit with some developer teams at IBM. And nowadays when I actually talk to them, performance is not really the first thing on their mind, for whatever reason, right? One thing that's really strongly on their mind is corruption, data getting corrupted. Because there are many reasons, especially to this drive towards running things more on commodity hardware. Commodity hardware is flaky. You can run Hadoop and these sort of things and give you some numbers, but if you're really going to trust your data on it, there can be bugs, the hardware is pretty flaky, there are firmware bugs that can happen, and system administrators might make a mistake because of which data gets corrupted. So this is something that they're very worried about. We are trying to apply some of this methodology to that context by automatically running these data integrity checkers, file system checker, database checker, and so on. Okay? Getting information from that and figuring out what other checks to run. Collecting snapshots to run these things is actually become very easy or very efficient today, because the storage community has made a whole bunch of progress on collecting snapshots. We're not going to spend too much time on that unless there are questions. The 2 other things I want to focus on are where do you run these experiments? The so-called harness for running experiments. So if this were to be your production database system, there's some clients running and you have tuned your system, maybe it's multi-core, multi-disk and whatnot, but often administrators will not actually let you do anything there, run experiments, never, right? So that got us thinking about where would be a place to run these experiments. Okay? So one answer might be, you can run it on a standby platform. And it turns out often these standby platforms, they keep, because if this primary were to die, this guy has to take over. The hardware configuration, at least in some scenarios, not all scenarios that we have seen, is very similar to what is there. Because if it dies, you have to actually go on. And I've seen scenarios where there's 3x investment in exact hardware production, standby and a development platform, all of which look pretty much the same as far as hardware goes. The most important thing, data is actually kept pretty much up to date, right? Because for experiments, we don't want to run it on very stale copies of the data. especially for parameter or for query level tuning. So this might be a resource, which is actually turns out to be heavily underutilized. Or on the cloud, right? Imagine your database might itself be actually running on the cloud. So getting these pay-as-you-go resources on the cloud, just taking a snapshot of your EC2 volume and then cloning it, firing up 10 different EC2 nodes to run these experiments is actually something which is very easily possible today. Just in a few lines of EC2 API scripting can actually do that. So what we have done is we have sort of developed, in some sense, I like to think of it as a policy interface and a runtime system, which so the DBA or the user, whoever it is, specifies. This is a language for specifying policies. Okay, so they can designate resources where experiments can be run, and they can designate with each of these resources conditions under which the resource can be used for experiments. And one of the first things we did is actually implement a policy like this in a context where the standby system is being used. The DBA says, look, I can let you run experiments on my standby under the condition the current resource utilization on the standby looks less than some particular value. And implicitly, one important thing we have to guarantee is if the standby or the primary were to fail, the fact that we are running experiments shouldn't increase the recovery time by any significant value. And what I have in this slide is actually a quick animation of that aspect. I'm already looking at the clock and it's 2:35. I just have this slide and another slide. Should I quickly try to go to the summary, or I can take 2 more minutes?
You can finish this.
Okay, so essentially this architecture that we have implemented, in fact using some technology on Solaris, although visualization is what we need. So imagine you have a production, you're actually doing log shipping and the standby is actually standing there. So by default what the standby will be doing is getting the logs, applying and being ready to take over when the primary actually dies, right? So what we can do when our system kicks in, it identifies an experiment, maybe it's a plan, maybe it's running an experiment with a different parameter configuration. The experiment scheduler will schedule an experiment, in which case we use a zones feature in Solaris to do this. We sort of take up what we call the home, which is the real use of that system, cut it down, and essentially and as few as 5 to 10% of resources on that machine is enough to take the logs and do its stuff. So that is kind of going on. So we don't stop the standby from doing its actual functionality, and we carve up the remaining resources into what we call the garage container. This is where experiments will get scheduled. And most importantly, we use in the ZFS file system that comes with Solaris the ability to do copy on write. So we don't create an entire copy of the data. So this guy is running experiments, this guy is keeping up to date, and only the blocks that change get updated. So literally they're sharing all the data. Of course, one thing we have to be very careful about is that, look, now maybe this is going to put a lot of I/O overhead that can affect what you see in here. Right? So there are some fidelity issues that have to be sort of taken into account, and that sort of happens when we get the result and then we are continuously monitoring. And there's, Solaris has really elegant low-cost monitoring. And we try to strip some of this noise out. And once we have this harness that we can run experiments, now what we are thinking is, why not actually have a declarative language where the admin or the user can sort of specify their experiments, the type of experiments they want to run, or more importantly, their objectives. And we are putting this, and the entire thing, the planning part, remember that workflow I showed you, the planning, the conducting, and the iteration, that part will be generated by our system automatically. We call this .x. Okay? And we're looking at 2 problem domains for this. The first one is the one I kind of showed you, which is the benchmarking and the tuning aspect, really focusing on mapping out a response surface either entirely or finding a good region. So this domain and the data corruption domain. So very likely, probably in the next couple of months, we'll actually have something to announce over here, where this whole corruption, the type of test, and running this automatically on the cloud will be able to actually have a tool called Emulate there. So that's it. I think in a quick summary, the need for experiments and automating this has always been there, right? I think now the infrastructure, especially with the cloud and its ability to kind of really carve out resource virtualization snapshots, that has made some of this possible. We have built a number of tools around this paradigm, and there are interesting higher level questions to think about. Should, for instance, should the system support experiments as a first-class citizen? rather than administrator actually coming and doing this. That's it. Thank you.
Any other questions?
In your definition of cardinality sets, you primarily concentrate on the cardinality as the equivalence metric. Independence assumption is another chronic problem. And independence assumption could be viewed as rather like cardinality. You can create similar equivalence class sets if that's your chronic problem, right? If you were to combine the two, is there anything better than the cross product or that you could do? Basically, there's both cardinality and independence assumption problem that are manifesting through the expressions.
So my answer is, so for us, this world, the world is sort of black and white between estimated cardinalities and accurate cardinalities. We don't peer deeper and actually at the level of why did the optimizer generate an incorrect cardinality estimate? Was it because of correlation? Was it because of independence assumption? Can we do some sampling to actually get a value? So essentially, Surjit and Vivek actually, and I guess Ravi, yes, they have actually done a whole bunch of work on using sampling and coming up with this confidence bounds and things like that. I've actually done some work myself. Somehow my feeling is it's all great research. But building a tool around that, it's taken us, for whatever reason, it's been very hard. So now why not just make things very simple? There's only black and white, estimated or accurate. I don't even try to, maybe the estimate is pretty accurate. Maybe it was actually based on a sample or something, right? Very accurate. So that is something we have not gone into. Maybe it would be interesting to add, but in some sense, that aspect which you're getting at, why the cardinality values are wrong, independence, and incorporating that somehow into the way we carve up the physical plant space and what we can, once we run a plant, what information that we can take from that and give it to other plants in terms of estimating their costs better. That's something which, frankly, we haven't thought about.
You're taking the independence assumption specifically. Independence assumption as it affects cardinality, you're right. Independence assumption as it is used in your cost function, you would not obviously create the equivalence class. It won't give you any. It won't discern that property.
Do you mean the independence in the sense that we are summing up the cost across different operators rather than operators running together and things like that?
Right. And that would have to be, just like another property that would have a different, it's not reflected in the cardinality, and how would you combine them? That's the question. Do you have any intuition on that?
Not really, but maybe we can understand what you have in mind better.
Well,
We can take this offline.
Yeah.
Any other final thoughts or questions? Thanks.